Well, okay, so now I think we are on. Okay, so last time, I think we basically talked about the constraint optimization. Maybe let me try to recap important concept of constraint optimization for the problem that we are going to consider. The objective function can be linear or nonlinear. The constraint can also be linear and nonlinear. Basically, we just assume that the decision variables taking continuous value and the objective function and the constraints are continuous and differentiable so that we can find the solution to the problem by using the information of gradient or Hessian, like first and second order derivatives. So we started with so-called equality constraint and saying that in order to take equality constraint into account, we need to construct some function called Lagrangian function with the multiplier, right, to take care of the equality constraint. And also we identify the so-called necessary condition in the gradient direction satisfy what? The gradient of your objective function at the stationary point should be the linear combination of the gradient of your equality constraints. And based on that, basically we try to find stationary point and then try to identify if those solutions are local minimal or local maximal or maybe non-optimal solutions. And then we also talked about what the inequality constraint. And in this case, we write it as g of x less than or equal to 0 in a standard form. And then the difficulty comes from where? I'm sorry? The inequality constraint, basically, we have to identify if the constraint is active or inactive, right? When we say the constraint is active, that means what? In the optimal solution, the equality constraint is true. On the other hand, if we say the constraint is inactive, that means what? Well, that means the inequality strict less than part is true, which means what? At this solution, you don't need to worry about this constraint because it's okay. It's not at the boundary of your solution. And to summarize, the necessary condition tells us what? If we construct a Lagrangian function, which I call L of x, and then what? Let me use lambda, and then maybe another multiplier I call mu. That include what? F of x, and then what? And then I will use what? Well, in this case, because I have a set of constraint h, which is a vector, so I have to use what? The vector notation for my multiplier. So in this case, I will say it's lambda transpose h of x. That's a set of equality constraints, and then I have a set of inequality constraints, which is what? Mu transpose g of x. Okay, so that's my multiplier. And then the necessary condition for a local maximal minimal should be what? Well, the partial derivative in this case should be written as the gradient with respect to variable vector x. So I will write a gradient for x, for f of x, and then what? Well, I will say plus lambda transpose. Well, in this case, it's not really a good way to write a gradient direction, because if I write, for instance, this gradient with respect to h of x, then I think some of you may get confused about this kind of notation, because in general, gradient is only with respect to a scalar objective function. But what if I have a set of equality constraints? if I still want to use gradient notation, which means for each part, I need to find a gradient. So overall, it looks like what? A matrix collecting the partial derivatives, which some people call that the Jacobian matrix. And also, if I want to write, there should be another constraint, which is mu transpose. I will also write like a gradient with respect to g of x. And then this should be 0, right? Which means the gradient direction can be written as a linear combination of this. But the level of difficulty is about what? To check the inequality constraints to be active or inactive. And that means the assumption is that I have this vector mu, which I say this is actually a vector. At some point, I need to know if at a solution which I have x star, mu star, and lambda star satisfy what? The necessary condition that we wrote there, the gradient direction of the gradient with respect to your objective function can be written as a linear combination of the gradient of your constraints, right? That's what we did. And then we say this vector, the multiplier for the inequality constraints have to be non-negative, right? And what? And also, if the inequality constraint is active, that means what? The equality part is true. That means g of x is actually 0, right? On the other hand, if g of x is not 0, then what? This mu has to be positive. It can, well, because if the other part is 0, if g of x star is 0, well, I will use gi. That means a particular inequality constraint is active, which means what? This mu I star will be, in general, positive. Okay? On the other hand, if gi x star is less than 0, that means the inequality is inactive, which will force this mu I star to be what? 0, right?
But why the mu I star has to be greater than 0? Can't it be 0 in that case? With gi of x star?
It can be 0, yeah.
But in general?
In general,
You're talking about in general.
Yeah.
But it can be 0.
Yeah, it can be 0, but in general it will not be. Why?
Because otherwise the mu term will have no value.
Well, because if your inequality looks like equality constraint, then it's treated like what you see, like this lambda, right? On the other hand, if you think about, if the equality part is true, then the multiplier in general will be either positive or negative. And then basically, in order to satisfy the inequality part, which means you have to check whether it's on the right side of the feasible region or not. So basically, if you combine these two things together, you can write this mu transpose g of x, of course, at this stationary point to be 0. Okay, so that's basically the condition for inequality constraint. And then I think last time we left a question about, for instance, if I have 10 constraints, there are 10 inequality constraints, then there will be what, like a 2 to the power of 10 possible configurations we have to check in order to see which solution is a stationary point, whether that's really optimal or not, right? And then we realize that this eventually becomes a combinatorial problem. That means as you increase the number of inequality constraints, the requirement to do the search will grow exponentially. And that's not a good way to handle the constraints. And then I ask all of you to think about what can we do in order to avoid exhaustive search for all the possible configurations in these so-called KKT conditions to find the local, the stationary points for inequality constraint optimization problem. So any idea about what to do? Need any discussions among your neighboring students? No? Well, I would suggest maybe 2 to 3 minutes discussion among students. You can find your neighbor, or if you want, you can also even stand up and walk around and try to. Just some discussion about some rough idea what you want to do. And I would say in general, engineering optimization is based on some intuitively appealing numerical technique that you can handle such a problem. And this is considered a very important aspect for the computational consideration on the constraint optimization.
Dr. Chen, could you restate the question just one more time?
Okay, yeah, the question is, in order to avoid exhaustively examining the inactive or active part of the equality constraints, can you design some method that doesn't really require to exhaustively check all the inactive or active part of the equality constraints? Basically, that's the goal. When you try to write a computer code or numerical algorithm to solve inequality constraints, how are you going to handle this? If, let's say, you have maybe 10 or 100 inequality constraints you have to take into account, you don't want to enumerate all the possible configurations. And is there any good way you can suggest to avoid doing that?
Well, in, say, like just a minimization problem,
yeah.
When you evaluate your function, if the function is actually outside of any of your bounds, could you just penalize it by adding a high value back to the function?
Yeah, that's a very good suggestion. So what David suggested is that when you have inequality constraint, when you put a solution that's not feasible, then what you want to do is just put some penalty to your original objective function. I think last time also Mr. Liu suggested the same idea by saying that if you don't satisfy the constraint, then you put some penalty function. Depending on how close you are to the constraint, maybe your penalty should be proportional to your suggested solution to where it becomes feasible in some distance metric. And that's some idea, I think, to handle the constraint optimization problem as an unconstrained optimization problem. Okay, so Well, I think what Bryce just mentioned is that if I have 1,000 inequality constraints, should I put like 100 penalty functions? Like I take the sum of 100 penalty functions to each constraint. What do you think? Yeah, I agree. We can do that. The unconstrained objective function becomes more complicated because it contains at least 1,000 terms. And also sometimes you may also want to penalize the function based on your necessary condition, based on your multiplier. And you can have a better way to handle this. For instance, you may not want to design like how large the penalty should be by doing some proper normalization. And in fact, that's really a great idea to do to convert constraint optimization to unconstrained optimization problem. And I tend to have maybe a new computer assignment dedicated to this so that you guys will have some idea about how to design a working algorithm to do this. And this is sometimes called the indirect approach, meaning that you don't handle the constraint directly. You change the constraint to some penalty function and then use unconstrained optimization technique to solve constrained optimization problem. Any other ideas? Yes?
Can we check to see if our set of constraints forms a convex set?
Can we check? What do you think? Yeah.
Yes.
Okay, yeah, yes. Usually if you can check the constraint set is convex, then what? You want to identify the problem is like a convex minimization problem.
Well, then you can just look for the extreme points of the polyhedron.
Okay. And in that case, would the problem become simpler?
Should be, yes.
Well, that's also a very important suggestion. What Saya just mentioned that if you think that the feasible set becomes some kind of polyhedron or some kind of convex set, then maybe we should hope that we just check the extreme points, the vertices along this, so that if we don't exhaustively search those vertices, then maybe we have a better way to find the extreme point efficiently. That's also a very interesting aspect, which I probably want to cover a little bit tonight. Any other idea?
I think if you went with the idea of doing some type of penalty functions or penalties, instead of just using a constant number to penalize it with, you probably could use some type of exponential so that it would have some type of gradient to it.
I think that's a very good suggestion. And in fact, we can design some adaptive penalty function that take these, like how the current solution close to the feasible set, how close that's close to the feasible set, or how close it will satisfy the necessary condition, the so-called KKT condition, based on evaluating the gradient or some other information available. So this can all be put into our design of the penalty function with respect to your multiplier. And for instance, for equality constraint, I think the easiest way to check how close to the equality part, maybe you just say, take the equality constraint and square and put some positive value to weight that, right? Well, for instance, I can say my augmented function will include f of x and then plus, for instance, I will say h of x, I will use maybe some weight a, and then, well, I cannot directly take square, right? So I will say, take each term and then do the square. I hope that each of you will essentially understand about the notation for this. Basically, the two norm in the Euclidean sense is just take each term, take the square for each term, and then take the sum for the square. Okay? And that's one way of taking care of the equality constraint. And for inequality constraint, then we have to penalize when the inequality part is violated, right? Is there any way you can do that?
We can consider the function as a difference of the two parts.
Okay. You can.
Because inequality is satisfied.
Okay, so if inequality is satisfied, if the inequality part is satisfied, then I shouldn't penalize. If it is violated, then I should, right? So it's based on what? Maybe I will say the negative sign of your constraint. For instance, I will write down something like if it's minus gj of x, for any j, if this thing, if g is negative, then this should be positive, then it satisfies the constraint, right? On the other hand, if it is positive, then it will violate the constraint, right? So for instance, you may say, if I just say plus this, would that work? Why not?
Once it's negative, then your fault just function will decrease.
Okay, so I shouldn't do that. Then what should I do? I will put the maximum of this and 0, right? Meaning that if it's negative, I shouldn't penalize, right? Would that work?
This function is not differentiable.
Well, then what do you do? Well, I think you can. Well, I think we had the example before. When you have find the maximum, you can always introduce what? Additional decision variable and or additional constraint to take care of that, right? So that's not an issue. So basically, this idea should work in general for introducing penalty to equality constraint. And then, of course, you need to put some weight b on top of that. And in fact, this is just straightforward way of doing this. And you can do better than this if you think carefully. But basically, the idea is still just to penalize whatever solution that violates the constraints. And the penalty depends on how far away your solution to maybe a close neighborhood of the feasible set. Okay, so this is one idea. And then Sayer also proposed another idea just to examine the structure of the problem. Any other suggestions up to this point? Well, in fact, you guys are very smart. You already talked about like 2 very important techniques on solving this constraint optimization problem. And the last idea, which is, I would say, not so direct, but later I hope if time allows, I will try to cover that, is to, for instance, still pursue along the gradient direction. However, because of the constraint, you cannot directly take the gradient. And you have to project your gradient direction to your feasible set, and then maybe do a gradient descent, like hill climbing, but under constraint, which is easier said than done. It has some technical difficulties involved that we have to overcome and to design a practical algorithm. And then, of course, a natural question to ask is, why do you believe that's better than exhaustively enumerate all the feasible configurations based on this KKT condition? Well, tonight, I hope that I will talk about a relatively simple constraint optimization, which is linear objective function and what? Linear constraints, which we call that what? If it's linear objective function and linear constraint, then we call the problem linear programming. Very good. So we will first talk about linear programming, and then also, like last time, Mr. Yu Liu mentioned that what if the decision variable is not like a continuous variable? It can only take discrete values, in particular only integer values. And then we will talk about integer programming and how, for instance, solving linear program may help us even to understand about integer program. And also, how can we solve the problem involve both continuous variable and integer variables? That's what we call mixed linear integer programming, even though the objective function is still linear and the constraints are linear, but because of that, the problem becomes harder. So that's basically what we want to do for tonight. Let's first look at the constraint optimization problem. In general, we assume that these f, g, h are real functions. They are continuous and they are differentiable. And the level of difficulty depends on, of course, whether you have convexity of the objective function, whether the feasible set is convex or not, depending on those kind of things. But in general, when we talk about the level of difficulty using computer algorithms to solve the problem, we have to classify that based on what? Like the time complexity versus the problem scale and the storage requirement versus the problem scale. Depending on, like, for instance, as you increase the number of decision variables, how difficult to achieve the optimal solution based on the computational resource. And then we classify the problem into the category of P and NP. P stands for deterministic polynomial time algorithm. And intuitively, you can say that means the computational requirement in general is a polynomial function of your decision variable. In this case, for instance, the number of constraints or the number of decision variables, things related to the scale of your problem. And then there's also another type of problem called non-deterministic polynomial time algorithm, which people call NP. Okay? And NP in general means what? You can show it is not a polynomial function. And most of the time in real engineering problem, it may be exponential or maybe super exponential, meaning that it grows much faster than a polynomial function in terms of the number of decision variables or constraints that determine the scale of your problem. And of course, for NP problem, we see it's harder to work with. And among those NP problems, people try to at least find some hardcore NP problems, which they call NP complete. And that means there are some problems which are shown to be what? Equivalent to some NP problem, meaning that if you can have a polynomial algorithm to solve one of these problems, then you basically can solve all of them because they can all be converted to the equivalent class in polynomial time. So that's a very important computational tool in computer science, in the theory of computation, to justify how difficult a problem is. And for instance, so-called traveling salesman problem is considered NP-complete problem. Can anyone give me another example that you heard about for so-called NP-complete problem?
Graph isomorphisms?
I'm sorry?
Graph isomorphisms?
Graph, can you explain a little bit?
If you have some nodes, then how many isoforms does the graph have?
Okay. And intuitively, why you think that's NP-complete?
It seems similar to the traveling salesman problem.
Okay, meaning that essentially you need to enumerate all possible configurations. Like in traveling salesman's problem, you want to find what would be the best route to cover all the places. And as you increase the number of cities you are going to cover, then the possible routes that you're going to enumerate will grow exponentially. And there's no essential way to reduce that without sacrificing the optimality of your solution. And same thing for what Saya just mentioned, this checking the graph that graph isomorphism, right? Checking like how many configurations you need to explore. It's more like somehow can be shown to be equivalent to some problem like traveling salesman. And these problems are called NP-complete. And some problems, we call that NP-hard, which means we don't know how to show that it is NP. But we can show it's at least as hard as some known NP problem. Meaning that, for instance, if you can solve traveling salesman problem, maybe you can solve my other optimization problem. However, that problem is as hard as traveling salesman problem, but maybe even harder. How hard, I don't know. And then we say that's NP hard. And in optimization course, of course, we can say if you have a problem which is shown to be in this NP-complete class, then there's no hope that you can use the existing computing device to find the optimal solution for large-scale problem. Make sense? And then what do we do in general if you know the problem is NP-hard?
Use a heuristic.
Very good. Use heuristic, which can be what?
Greedy.
Which can be anything like greedy, or later we are going to cover some approaches, and greedy or local search, and some other things like genetic algorithm, simulated annealing, taboo search, and some other things. And what else? And sometimes we have to settle with so-called suboptimal solution. And by saying suboptimal, and some people may say it means non-optimal solution. Well, that's not really the right word because, for instance, I say, well, this is the best solution I can find based on my computing capability. Let's say I run my genetic algorithm for 3 days, and here's the best solution to your problem, and then you deliver to your immediate supervisor. Do you think that's a good justification? We should settle with that solution? Yes? You think so?
I think because it is
Because you're saying nobody else can get a better solution at this point, so we should settle with that. Well, I would say that's not really a good way to justify. Most of the time, if you know, for instance, I say, well, I know this is not optimal solution, but I can guarantee you if you can find the optimal solution, it cannot be 20% better than my solution. Then that's considered a suboptimal solution you can present. to people saying, well, I tried my best. You know this is an NP-hard problem. I'm 80% close to the optimal, at least. Maybe this is already optimal, but I will never know. And that's considered suboptimal algorithm with quantifiable performance guarantee. And how to do that? Well, in general, it's a much difficult problem than what I can cover in this course, but I will try to give you some idea in general what people do to approach suboptimal solution with so-called approximate algorithm or maybe randomization or de-randomization techniques, which maybe only at the very end of this course I will introduce some technique that's considered modern techniques for optimization. And why do we talk about this? Because later when we get into some optimization problem, we will see that by changing the decision variable from a continuous to discrete, the problem in fact becomes much harder than what you can think of in terms of finding the optimal solution. So we will get into that shortly. And let's look at the classification of optimization problem with real variables. Of course, one special case is called linear program, which is considered what? The simplest constraint optimization problem. Remember, for unconstrained optimization problem, we started with what? Single variable, and then we talked about line search and things related to how to search the peak or valley in one dimension. And then for constraint optimization, of course, we can talk about the linear objective function and linear constraints. For unconstrained optimization, we don't talk about linear objective function. Why? Because there's no constraint, then linear objective function doesn't make too much sense to you, right? At least you need to have maybe a quadratic function, which is considered the easiest way to visualize some convex function without constraints. And now, for linear program, which is considered easy, and also it's a special case of convex program, it's usually fast to solve, but we will spend some time talking about the techniques we are going to learn solving linear programming and how that may affect us in terms of examining the constraints which are active or inactive for nonlinear inequality constraints. If the constraint optimization is a convex problem, and later we are going to say for convex problem, you know there's like a unique global minimal solution you can find, and that there's a hope that by following the gradient descent direction, you can achieve the global minimum. But for non-convex problems, they are usually harder, and in general, there's no guarantee to find the global optimal solution. So that's basically the overall picture about how the optimization problem looks like. And then, of course, there's this so-called integer program, which means the decision variables can only be integer. And in that case, the computational complexity is in general NP-hard. I notice the term, I didn't say it's NP-complete. Why? Because there's no way I can map any integer program into a no NP-complete class. So I just say, in general, it's hard. And then for mixed integer linear program, it is also in general NP-hard, which means you cannot find the optimal solution if the problem is of very large size. However, there are many problems in real engineering context can be solved surprisingly quickly. And also there are some known software packages that handle this very efficiently. For instance, this so-called Cplex is one important tool to handle so-called mixed linear integer linear programming problem. Okay, so let's think about how can we solve a linear program. And we know that when you have a linear objective function, then the level set looks like what? The contour will be a straight line, right? Because you have linear objective function. And what about constraint? Those, if you can put constraint into the inequality side, meaning that you have this what? Half plane cutting your space, right? Basically, you can think about each constraint is like what? Some kind of cutting plane on the side, okay? And then, of course, if you want to satisfy all the constraints, then you have to think about the intersection among those half planes. That's what people call the polyhedron of the feasible set for the linear program. And the optimal solution must be at some intersection of the constraints. And of course, that's assuming the original linear program has been converted into a proper standard form so that you can run the computer program to solve. And of course, in general, you can find the intersection for different hyperplanes in the constraints. And that basically, you just change the inequality to equality and then solve for linear equations. And solving linear equations is considered not a difficult problem. However, there is always a level of difficulty in terms of how you jump from one extreme point to another. And of course, originally, I think the linear program was mainly designed for solving some industrial problem where you can use computer to solve by so-called simplex method. That was originally designed to solve this kind of optimization problem where you take the inner product between C and X and then subject to AX less than or equal to B for decision variables X greater than or equal to 0. But one level of difficulty is whether you can even find a feasible solution in this simplex. How are you going to guarantee you can, in fact, find a feasible solution? Well, here's a very interesting example that I think I took from some art where if you look at this architecture, is this system optimal? Well, can you see any problem with this?
It's more than.
Why?
It's infinite. Well, the water supplies itself.
Well, if you examine carefully, which I would hope that maybe after class, if you want to spend some time looking into this, then you will see that, in fact, this descent direction has some kind of self-contradicting to its level, so that the system may not be feasible at all to be constructed like this. And same thing when you think about an optimization problem, where you specify the problem, you don't even know what the feasible set may look like. If it's an empty set, then you don't have a well-defined optimization problem, but how do you know that? Is there any way you can efficiently test whether there exists a feasible solution to the optimization problem? I'm sorry? What is this system? That's just some, I would say some paint by some about a building which is supposed to look like this, but when you look carefully, you will find some problem in this design where apparently the level set contradict, this system eventually you conclude it's not feasible. But when you think about an optimization problem, the first thing you want to verify is whether you can find a solution satisfy all the constraints or not, right? And is there any efficient way to do that? If I have all constraints are linear, how should I do that? I think what you suggest is that assume all constraints are active and try to solve that first. Is that what you're trying to do? If I have 1,000 constraints, you're saying that I set all the equality constraints to be true and then try to solve for x?
Maybe. I don't know how to handle the inequality part now that I'm thinking about it.
Okay. Yes.
Okay. Just like this system, I mean, if you just look at it, you can't do it. So what else do you? I mean.
Well, in this example, of course, you have to virtually tour along the building to see if there's any problem later to contradict to this side. But when you have a set of linear constraints, are you going to test each constraint to be active or inactive? Of course, if you do that, then it goes back to what we just mentioned in examining the inequality constraint for so-called Cohen-Tucker conditions. In the original problem, we say that's really a computational expensive way to do the exhaustive enumeration, right? But now we are trying to see if for linear problem, is there any better way we can examine the constraints to see if there's any feasible.
You have some equality constraints and you have some inequality constraints.
Yeah, let's assume all these are inequality constraints.
Okay.
Yes?
Can't you build a polyhedron and just find the area of a polyhedron?
Okay, so build a polyhedron, I think that's doable because you can say the equality constraint already specified that. And then, but how do you test it's really a polyhedron? It's not an empty set.
You show the existence of a point in the polyhedron.
Okay, but how do you find such a point? You make it up? Okay. You need to, of course, if you have, let's say, 10,000 inequality constraints, which for industrial optimization problem may be a reasonable size to talk about. And still, you need to write a computer code to first find a feasible solution. How do you achieve that? Well, that has nothing to do with this slide, so. Well, remember, we are talking about linear constraint and linear inequality conditions, and we assume the decision variables are non-negative, right? Then what can we do? At least in this particular setting, we have a way to do that, right? We start from where? Decision variable to be all 0, right? And then if that's not feasible, then there's no way you can improve. If that is feasible, then what? In general, you can improve along what? The direction on the positive, along the positive axis, right?
Why is the whole problem not feasible?
Well, we assume the decision variable is non-negative. All the decision variables are non-negative, right? And then, let me see. If the,
for example, you have a negative x is smaller than negative 2. If you put 0 in,
it's not okay.
It's not feasible. But of course,
It's positive. Yeah, maybe I probably should not really just examine this point, right? But what I'm saying is you can start from this origin and then what? Check specific direction on your inequality constraint. And then what? Improve upon that. If for each variable you have a positive region to satisfy the inequality constraint, then eventually you take just the minimal value and then cover that constraint and then keep going, right? Meaning that, like in Mr. Yu Liu's example, if you say it has to be less than or equal to, if decision variable x1 has to be less than or equal to 2, then it's just you move your feasible region to 2 and then just keep going, right? And same thing for other decision variables. And by doing that, you don't have to enumerate all the configurations. You just examine one constraint at a time. And then what? At the very end, if you have empty set, then it's not feasible. If you have anything below that's positive value, then it's feasible. That means for each decision variable, you start from 0, and then just try to explore the positive axis until it becomes feasible. Make sense? And in general, you can see that you have constraints which will basically make the feasible region looks like this shaded area in this particular example. And in general, you can say the simplex begins in the origin, and then you can what? Move to the front where this is x plus y greater than or equal to 2. So only above this line on the right-hand side, you have feasible, right? And then maybe you can say I move to this point from A to B to make. I'm sorry? Well, you start from A, and then in order to be feasible with respect to the first constraint, you move to B for x. You mean this line or?
Yes, sir. The bottom one, no.
This one.
Going up in a positive slope.
This one. 2x plus 2x minus 1 greater than.
No.
Minus x plus 2y greater than or equal to 0. You see 3 constraints. Sorry. This is greater than or equal to 1. So.
Yeah, so it's got to have a.
So it should. So yeah, I think I agree. This should be up. Yeah, this should be okay. Yeah, because I draw this like zero. If this is 1, they should go up to 1. Yeah. Yeah. Yeah, I agree. Yeah, this should be 0 in this figure because it's minus x plus 2y greater than or equal to 0. And then basically when you move to B, and then if you take the other 2 constraints into account, you can only move along this direction up to some point, let's say C, and then, of course, in this case, C becomes feasible. And, well, I guess there's some problem with the font in this, I think in this PowerPoint.
Yeah, it looks like you had a 1. You know what it looks like? It looks like you shouldn't have a 1 there.
Yeah.
If you look at your next one, matrix form, you don't have it in the equality form equal to. Well, we got S3 is equal to greater than 1. Yeah, that's right.
Well, if you look at this constraint, these constraints are inequality constraint but greater than or equal to some value that's not 0. And then we try to introduce some so-called slack variable to make it basically 0. And then by introducing this additional variable Si, we can basically put this into a standard form like this, where you have x and y, and then you have 3 slack variables, S1, S2, S3, taking care of these 3 inequality constraints, so that I can make it like Ax equals to 0. Make sense? So basically, you can say inequality constraints can be changed to equality constraints by introducing additional variable, so that you can make linear program to be in a standard form. And I think I'm missing some value on the front. When you print out, is it the same like this? It looks different. Yeah, I see. So I think it's just some fonts are missing in the display, so I couldn't. Yeah, I couldn't see a great way to represent this tableau in the simplex. So basically, when you have a linear program, when you have a linear programming problem, you want to change the problem into a standard form so that you can call a linear program routine like a package, or you can basically design a generic algorithm to solve the problem. And the technique that you introduce is some so-called slack variable to make the inequality constraint to be equality constraint. And then you put this into a tabular form, which I cannot really present very well in this. I hope then maybe next time I'm going to do it on board to have better ways to distinguish between so-called basic and non-basic variables. And if you have the printout, you probably can see, but this is definitely not a good way to distinguish anything clearly. I'm sorry?
This is not that printed.
Oh, you are going one step further to the next lecture. Okay. So I think some of you did this, and you have this S1, S2, S3 on the row, and then you have X and Y on the column, and then the coefficients are inside, which I think there's some missing font used in the presentation that I couldn't figure out why this is the case. This S1, S2, S3 are the basic variables, and these X and Y are non-basic variables. And essentially, basic variables are the additional variables you introduced to make inequality constraint to be equality constraints. And then non-basic variables are things that really related to your decision in the linear program. And then based on that, you can basically change the problem into a standard form by construct a table, and some people use so-called tableau to rewrite the system into a form that involves only the equality constraint on these non-basic variables. And the basic variables sometimes are called dependent variables, depending on the context. Like if people in management science or working in operation research, they probably use some term that's not really in the strict mathematical sense very accurate. But basically, once you change it to a problem like this, you say the constraint become ax equals to 0, and then you have the range for you basic variable si, and you can basically solve linear program by so-called simplex method. And the simplex method basically is to first construct the standard form, the table, and then order these variables, and then try to satisfy this one at a time. If you cannot satisfy, then you rotate, perform so-called pivoting operation between variable xi and xj. And then basically it's a way to jump from one vertex to another. And if you satisfy all the variables, then essentially you end up with the final solution. That really minimize your objective function, because each step you try to go along the direction, not really greedy, but try to basically change the variable from unsatisfiable to the satisfiable by a critical rotation. And another, which is slightly different from this searching on the extreme point, another method which is also equally important is called interior point method. It is not an algorithm that directly gets into the vertices and then jump around this. It's based on starting from some interior point, and each step try to improve a little bit by changing the so-called barrier function to the original linear program, and then basically eventually approach to the to one extreme point. Hopefully that's the optimal solution. And this technique, of course, has a name called interior point method. It's based on either primal or dual formulation, and it can basically apply some kind of either standard iterative method or even going through so-called Newton step, which is based on like quadratic convergence, but requires some information on the second order derivative of the barrier function. And the benefit of doing this is that essentially this works better than the simplex method with certifiable optimality. Meaning that originally, the simplex method was proposed by, by George Danzig, who actually studied a lot of important problems of industrial defense, operational research, and then proposed an efficient technique to solve linear program. And at that time, people already applied the method to many real engineering problems and found the optimal solution efficiently. However, later, when this computational complexity concept was introduced later by computer theorists, people realized that the simplex method can have exponential complexity to some linear program problem, even though those problems are rarely seen in real life, but some man-made problem can make this simplex method basically pivoting through exponentially growth of the vertices before approaching to the optimal solution. And then some people feel bad because if the algorithm doesn't exhibit some efficient computational requirement, then there's a worry that in real life the method may fail to some new problem that we don't know. And of course, later some Russian mathematician invented another type of so-called elliptic type of method, which proved to be of polynomial complexity. On the other hand, that method is not as good as the simplex method in the implementation. And only in the late 1970s, in the last century, I think Kamaka and some other mathematicians, applied mathematicians, proposed so-called interior point method, which shows to be effective in terms of the computational complexity is polynomial, and also the algorithm works as good as well as simplex method. So this becomes like a breakthrough in linear programming. And also the formulation is quite general so that even some nonlinear constraint optimization problem can be still addressed by interior point method. So that's why later I may spend some time to talk about the mathematical details on how this method works. So now, if you look at the linear program, the optimization package for linear program, most of the state-of-the-art linear programming package will first ask you to identify the problem type. For instance, if the constraints are sparse in terms of the decision variables or not sparse, whether a lot of things related to which algorithm you want to pick. And most of the time, you may want to consider so-called primordial interior point method for solving linear program instead of simplex, especially for very large-scale linear program. And now we just try to switch the gear to another set of problem where you have linear objective function and linear constraint, but decision variable can only take integer values. And in that case, in general, what do you do? I think most people would just try to run a computer program to do what? Enumeration, right? Because, for instance, if x1 can take value 0, 1, and 2, then the first stage is just say set x1 to 0, and the x2 can also take value from 0, 1, and 2. And then basically, you construct some kind of tree structure to search on this. But this exhaustive search may not be a good way to solve most of the problem involve discrete decision variables. And I think the next lecture, we are going to talk about dynamic programming, which is considered a very important technique to solve optimization with respect to discrete variables. And this technique, even though it's some people call brute force technique to solve the optimization problem, may be effective if your problem is of small scale. If you have huge computational resource to be spent on this, it guarantees to find a feasible solution in most of the cases. And also because you only consider integer, check feasibility is relatively easy. However, to get the optimal solution, you essentially have to enumerate every feasible solution, which is considered to be exponential growth in computational time. So that's basically the problem we are going to talk about after a short break. And basically, we realize that linear program is relatively easy, but when you change the decision variable to be integer, the problem becomes more difficult. And then a natural question to ask is there any way we can do it more efficiently. So let's take a short break, and then we will revisit this.
That interior point method, the starting point must be feasible.
Yes.
In that.
In the interior,
yeah.
From the interior.
Yeah, okay.
Yes.
Well, okay. Sometimes maybe the start point is not easy to.
To find a feasible solution is not easy. Yeah.
Okay.
But most of the time, finding a feasible solution should be doable task. You can always start from the origin and then just go along each coordinate of your decision variable to search, and then change back and forth, so that you don't have to enumerate all the possible configurations of your active or inactive constraints.
Okay. Yeah.
Yeah, I would prefer that. And can you come a little bit early, because I have another discussion with the REU student at 1:30.
So 12:30.
12:30. Yeah, that should work for me. Okay, thanks. Yeah, also can bring the file to, maybe if I'm not in my office, then probably I'm in the SL lab.
Okay.
Yeah, so you can bring your file if you want. Yeah, 617. Yeah. So you're looking at the references from the textbook and try to see it.
Yeah. So even for the integer linear program, there is still not a general way to solve the problem.
No. Well,
not to mention the quadratic also.
Well, in general, integer programming is considered hard, but mixed linear integer programming can be relatively easy. And also, it's more important for a lot of engineering optimization problems.
Mixed one is even easier.
Yeah, we'll see. Because, for instance, this, of course, depending on the problem structure, the size of the problem, and things like that. But still, because, for instance, integer programming means all the decision variables have to be integer. And here, maybe only a few decision variables have to take integer values. Others are taking continuous values.
Of course, if you it says this decision variable is the same size, of course, one has some portion of a portion of the decision variable is continuous, then that's easier.
Well, not always true. What I'm saying is, if it's not linear mixed integer programming, if it's non-linear, then I have to take back whatever I said, because it's as hard as the integer program, and sometimes even harder. Because you can always make the continuous variable to be non-smooth, so that none of the existing technique works.
So for linear case, there's still no general method.
No, but still, some methods are provably good with some nice properties, and some methods are based on some important optimization idea which could be applicable to more complicated cases. And that's why I intend to cover only the essential ingredient for the engineering optimization techniques, which are useful for, hopefully, for the research that you're working on.
So you mean all the methods finally convert to search in some direction or in some ways?
Yes, I totally agree.
So the difference is how many numbers, how many points do you need to search?
Yeah, like how many function evaluations do you need? What additional information do you need besides the objective function? If you say, I can only evaluate the objective function, nothing else, then the problem is, in general, very hard. But if you say, at least I can characterize the gradient direction at any point, then it's relatively easier. Okay, so let's look at a linear integer programming problem where if we don't consider the integer constraint on the variable x, y, and x2, we have so-called standard linear program. And in that case, you can say that the direction to increase the objective function is along this red arrow, so that if we want to minimize C transpose X, we should go along this direction, okay? And then also we say the constraint is basically like this, the intersection of the half planes characterized by all these straight lines, so that only this area of this polyhedron is considered feasible. So if we go along this direction to some extreme point, this point will be the best solution to the linear program among all these different vertices along this direction. If you go along this direction, that's the extreme point. So what can we do? For instance, we say within this area, we have only these integers, okay? And then this integer is closest to this extreme point, so this should be the integer solution, right? This should be the integer solution to the original linear program, okay? Okay, and for instance, one natural idea is, let's say I solve the linear program. That we know you have an efficient way to do that, right? And then you say find the closest integer solution. And then I think Livy asked me the very good question, how do you know that's close, right? Euclidean distance. Okay, so first is like, how do you know which integer solution has the closest Euclidean distance to your linear program solution? You do brute force. That's doable, but would that work? That we can have some difficult cases where, for instance, if you think about, still this red arrow indicate the direction we should go in terms of the objective function, okay? And then this line and this line highlight the constraints so that we have one extreme point at a linear, that's the linear program solution. Okay, so that's what we get. Okay, and now if you look at the closest integer solutions, these 4 points, they are not feasible. Okay, so what can you do? Of course, you have to go to this area. You say this integer solution is the closest to this point. Okay, but can you always check this to say that's the optimal?
Although this integer solution is feasible, and it is nearest
to this, yeah.
But I'm not sure. I think this is not necessarily the optimal solution.
Well, that later we will see. But what is important in this example, you will see is that this solution, of course, is a non-integer solution, but it is actually lower bounding your optimal solution, meaning that you cannot do better than this if you put integer constraint to the problem. Agree? Okay, so at least the linear program solution provides some way of lower bounding your integer program solution, meaning that you can say even though this is not achievable, but at least it's an indication on how far you are to some optimal value. Make sense? Well, in this case, you can say that this integer solution can be arbitrarily far away from this linear program solution, right? But still, this is an indication on this is if I don't have integer constraint, that's the best. That's the best I should achieve. Okay? Is that useful? Yeah, I would say so. Why? For instance, you can always combine the idea of linear programming and integer programming. Okay? Meaning what? First, if you don't consider the integer constraint, you can always solve the linear programming problem, right? And then your solution can be fractional, meaning that your solution will not be integer. And then what? And then you take integer constraint into account. Okay? For instance, if you think about, still in this example, we know this area is the feasible region, right? And this red arrow indicates the direction we should go. Okay? And then if you think about, these vertices are extreme points from the linear programming. And we would hope that this is the solution we have from the linear program. And then the question is, how do you find an integer solution within the feasible set close to this solution to the linear program, right? How to find that solution? Well, one idea you can say is to now you branch this to the nearest integers. For instance, if you think about this guy has to take integer values. This x2 has to take integer values. Then when you take that into account, then this is the solution of the linear program when you have to take integer values for x2. That's this point, okay? And then what? this is also when x2 has to take integer values, that's also the linear program for x1. And then if you think about, then if you now you count the integers, this guy or this guy, of course, should be this guy, right? Then if x1 has to take integers, then it has to be this. So the procedure would be what? You get the relaxed linear programming solution, then you enforce x2 to take integer value, and then basically find the best solution in terms of the x1, and then see if, and then also you do the same thing for x1, but then a question is, which way should you go? You go x1 first or x2 first? Does it matter? Well, in real problem, it does, because the solution could be different. You limit x2 to take an integer and then get to x1. Sometimes the solution can be different from the other way around. And overall, of course, you can always branch and bound your solution depending on how you solve the problem. In this particular example, we can actually do this branch and bound. And the idea is that every time you solve a problem by looking at the relaxed linear program, you can always find a lower bound. And then the feasible solution will give you the upper bound. And then if you have the lower bound and the upper bound, then what? You only branch whenever there's a room within this bound, right? If there's no room within this bound, then you don't need to do any branch, right? Meaning that your solution is already optimal in the integer with integer constraint. Well, let's walk through this example. This is the original problem. And then let's say we can do the branch and bound based on the original problem that we wrote here, which in the first case, if you solve x1, x2 without integer constraint, you end up with x1 3.4, x2 2.3, okay? And then you evaluate your objective function. That's considered what? The lower bound, right? Okay, and then what? And then you need to make it feasible, right, for x1 to be integer. So in that case, if you say I check either x1 is 3 or and then x2, now if x1 is 3 and then x2, still I don't put integer constraint to the linear program, I end up with x2 equals to 2.6, okay? And then I can evaluate my linear program solution, which is J1, okay? And what do you think about J0 and J1? Which one, if I want to maximize my objective function, which one should be larger? This one or this one? Without constraint, I get larger value, right? And then with one constraint, I should have smaller value. And of course, I could also fix this part by saying that x1 is greater than or equal to 4 plus the original problem, and then I get another value. In this case, I have somehow this I know should be feasible, right? And this I don't know, but this should be the best hope I can get. And then from these two branches, basically, I get the difference of the objective function. And then I will know, like later when you branch for x2, whether you need to go further or not. And of course, you can also do another case for x2 is less than or equal to 2, or x2 is greater than or equal to 3. So in fact, you have what? 4 different cases on this. Because you have non-integer solution, x1 is 3.4 and x2 is 2.3. So basically, you try to round it to 3 and 4, and this is 2 and 3, right? So if you look at here, this is the branch for x2, 2 and 3, and x1, 3 and 4. Okay, and essentially, some of these will not be feasible, right? And whenever you get a solution above or below, then basically your objective function, you know the optimal solution will be what? Within this point and this point. That's basically what I try to say. Make sense? Because you can only take integer solution, what I'm trying to say is if you consider the integer constraint on this x2, then that's the solution when x2 is when x2 equals to 2, and this is when x2 equals to 3. And then you have, let me see, if x2 is 2 and it is 3, then you have these two solutions. And then basically, when you have the optimal solution that can be bounded within this two range, then you have the integer programming solution based on this branch and bound technique. So here's just a brief summary of how the branch and bound algorithm works. Of course, you need to solve the linear programming relaxation problem to get a lower bound on the cost of the current branch. If I minimize C transpose X, then basically you cannot get the objective function smaller than the relaxed optimization problem, because you need to take integer constraint into account. I don't have such a constraint. Then I have this lower bound. And if this solution exceeds the upper bound, then of course you don't need to branch further. And if the solution is integer, then you replace it with the upper bound on the cost. And then basically this is like how you do the branch, and then you place a bound on your branch. And whenever you have two branched problem, by adding a new constraint to the original problem, then basically you select integer variable with fractional linear programming solution, and then you add integer constraint to the original linear programming. Of course, you can start from x1, or you can start from x2, and you repeat this procedure until no branch remains. Then the solution is guaranteed to be optimal. Is that clear or not really? This is not in the textbook. This part basically is about mixed linear integer program, which in the textbook, it only covers the decision variables are all continuous. And then, for instance, I think some of you may work into real engineer optimization problem like this. And you need to know, in general, how to handle such a problem.
So, in this case, the branching first, when we took x1, put a constraint on x1, and then when we put a constraint on x2. So, should we do it in both ways, where we put the constraint on x2 before we put the constraint on x1, and see how many branches we get in both cases?
Well, you can start from putting integer constraint on x1 first and then x2. Or you can start from x2 first and then x1. You have two different ways to do branch and bound. Which one is better, you never know. That's the problem, because the complexity, of course, depends on what? On how the gap between the upper and lower bound. That will essentially eliminate certain branches. If you have to branch all variables, which means what? Essentially, you are enumerating all the possible configurations. I think the analogy is like what? You can think about each decision variable is like you have inequality constraint, which you want to test whether that's inactive or active. You have two choices, right? And if everything you need to do is based on what? You branch, and then you branch again, and then you branch again. If it's a tree structure, then in general it's bad. Maybe let me try to illustrate a little bit based on this. If I have decision variables, let's say if I have decision variables x1, x2, up to xn, okay? And then, for instance, if I branch x1, I may need two things, right? This is, for instance, I can say this is x1 is 3, and then x1 is 4. Okay, and then I'm talking about what? Another branch for x2, right? This is like x2 is 2, x2 is 3, for instance. And then this, I can have to do another branch. This is also x2 is 2, and then x2 is 3, right? And then if I have x3, you can envision it go like this. And then eventually this tree will have what? 2 to the power of n nodes, right? And that's not what we want to see, right? Why this branch and bound technique may work? Because at certain point, if I know this part, there's no need to branch further because my upper lower bound already collapsed to the same thing. Then you don't have to branch to other variables because other variables won't play any role. Then essentially you can reduce your complexity significantly. Okay? And that's basically the key whenever you have this branch and bound method, how it may work, depending on the choice of specific sequence. Yes?
Theoretically, it can actually do 2 to the n nodes in the worst case scenario.
Yes. Okay. Theoretically. And in practice, there are different ways to construct branch and bound function. For instance, I think some computer theorists, they try to basically use what? Some heuristic function to determine when to branch. Because, for instance, you chose x1 or choose x2 or choose, basically the first round, you can always choose relaxed linear program to see which one has more potential. And then basically do the first round selection on the branch only by some kind of greedy heuristic. For instance, if you say the upper and lower bound, the gap is greater than some threshold, then you choose what to do. And of course, that's just one way of doing this. There are different ways. For instance, even some type of search technique like a breadth first search or depth first search or some heuristic search called A star. These are things you could do to just have a better guideline on how you make branches in the sequence. But yes, in general, the problem is still NP hard. So there's no hope that like you have a generic algorithm that can reduce the complexity. But hopefully, by using this idea, you can already have a better way to handle mixed linear, integer linear program. And also try to sometimes not get into a suboptimal solution where you don't know how far away you are to the optimal. And here, at least you have an indicator based on what? Relaxed linear optimization problem. Basically, linear program, you can always find the optimal solution. You know that's not achievable, but you can compare how close you are right now. Okay? And this is just a simple illustration on the order that does matter in terms of the performance when you do branch and bound. You can think about all solutions cause branch to stop. Each feasible solution is just an upper bound on the optimal cost, so that may allow you to eliminate certain nodes. And if you look at this extreme case, this is the linear program solution. If you branch x1, then x2, what will happen is that you go like what? You branch x1 and then x2, or you branch x2 and then x1. Which way do you prefer? For this example, why x1? Well, basically branch means what? You apply the integer constraint to that variable, right? You go x1 first or you go x2 first. If this is the linear program solution, and then the feasible region is kind of this, like a slant area. If you branch x1 first, what will happen? x2 will basically guide you very fast to this, right? And then what? You can quickly upper lower bound to this area so that you know this would be the optimal solution, right? On the other hand, if you branch x2 first, you may have to struggle until you branch x1 to reconcile that optimal solution. So that's basically the heuristic in this example. But in real engineering application, you don't know. So that's why if you have any prior knowledge about the feasible region to be of this shape, then of course you would easily make your decision. But that's the difficulty is for large scale problem you don't know. And that's why still there are some advanced techniques to determine a good branch and bound sequence in order to solve the problem with a better idea. And of course, another possible improvement along this line is based on so-called cutting plane method, which is also considered a very important modern technique to do optimization. So the idea is from that this branch and bound basically you can think about is like you have integer constraint like along different axes in the decision variable. And sometimes you may want to tighten your constraint of the relaxed linear programming by introducing what? Additional plane to cut your feasible set. And this may help to eliminate some non-integer solutions to your problem. And basically by doing that, you can think about all the integer solutions originally feasible will be remaining feasible, but some integer solution will be cut based on the additional plane. Okay, so for instance, this is just a simple illustration of how the cutting plane method may work. If you look at this linear program, you have this constraint and this constraint. The feasible area is this positive area originally, and then these are the integer values. Okay? So what we are trying to do is to introduce another plane. This is so-called added plane to cut the feasible set so that this area, originally this is the extreme point to the linear program solution. And then when you add this cut, then of course you have two extreme points here. That's not the key. The key is that by doing this, you eliminate some integer solutions automatically from this, so that original integer solution will be remaining feasible. If that's feasible, it is still feasible. But by doing this cut, in fact, we shrink the region so that it's relatively easier to find an integer solution. When you cut this more and more, essentially, it will approach to a nearest integer, which will be the optimal solution, as quickly as possible. And that idea, of course, also works when you have inequality constraints. And the reason for doing that is to what? Try to start from some feasible region and then approach to the optimal solution as quickly as you can. So this is one idea that's very important in modern optimization technique based on so-called cutting plane. And of course, a relevant question to ask is how do you design the cutting plane so that you can guarantee that all feasible solutions are remaining feasible, and also how to improve your cutting plane so that the solution will essentially approach to what you're looking for. And of course, because this is actually not essentially covered in the textbook, so basically I wouldn't ask you to have very thorough understanding on this, but bear in mind, if you have real engineer optimization problem, you may need to look into some commercial or educational software like Cplex is considered very important software to handle linear mixed integer program. It contains many improvements to the existing technique based on the branch and bound. Basically, it does a lot of problem reduction, variable organization, pre-processing, and heuristics for node selection to do the branch and bound. Also introduce different type of cutting planes based on flow covers, rerounding, and some other techniques, which basically try to solve the problem with a good suboptimal solution. And the package, basically, you can say, is very good in terms of interfacing with MATLAB. And then basically, you have this developing environment. This AMPL is a standard programming interface that can basically call some core function in Cplex and then doing some optimization routine very conveniently. And unfortunately, this university does not have any license to this software. So you can only do if you want, you can only do a trial on the demo version of this. And I don't have any way to demonstrate this by any computer assignment with the software. But here's just a simple example to show you, in general, if you have optimization problem like this, what you need to how you formulate the problem and what you need to do to use some good software optimization software tools to solve the problem. And this is like a task assignment problem. These are things you want to assign to cover these stars. You can say you want to find a good flight path to avoid obstacle and also cover this. And then basically, you want to minimize the mission completion time for a collaborative, maybe surveillance to cover these spots. All the tasks must be assigned, meaning that all these stars will have to be covered. Of course, you have some timing constraints between those tasks. And also the obstacles should be avoided. And what type of problem is this? Nonlinear optimization? Understand? I hope everyone understands about the problem. And why this problem is hard? Well, no. What I'm saying, all these stars have to be covered. You have to design which plane flies which parts to cover which star, so that overall the mission completion time will be minimized. And you have to avoid the obstacle, so that basically you need to think about each plane may just try to find the closest star first. For instance, that's one way of doing the heuristic, but that may not work. For instance, some star may be very difficult for all of them. You cannot say, let each of these guys just handle the easy ones. Of course, you can go the other way around. Say, find the most difficult star and try to assign the closest plane. There are different heuristics you can explore, right? On the other hand, those heuristics cannot guarantee any optimality in this case. So this is, in fact, an NP-hard problem. Instead of just consider like 6 tasks for 6 planes, if you think about, you have to consider what? All possible permutations of the possible star sequences. And even if you think about 2 aircraft, 6 stars, and then how many permutations we are talking about, this is already 4,320 solutions you have to search. And then the timing constraint, of course, is based on the shortest paths through tasks. And then if you only consider the shortest paths problem, which later we are going to show, finding the shortest paths is not very difficult. It can be solved by, I think Nan already read my notes for next time. Dynamic programming. Yeah, that's a very important technique next time we are going to talk about. But in this case, shortest paths may not be the optimal solution at all. Can you see that? Well, it's difficult to visualize, but we talk about like the team need to have the minimum mission completion time. Doesn't necessarily minimize the overall traveling path. Meaning that, for instance, if one guy covers maybe 4 stars, the other covers 3 with a different alternative, it could be better maybe than they do this way. And of course, if you do all the enumerations, you are facing this combinatorial exponential growth of your feasible solution, of the set of your feasible solution. So this is considered a very difficult problem. And if you think about the task assignment problem, you can basically write like the description file for the optimization problem in this AMPL interface. and then try to call this simplex routine to solve the problem. And you can even interface with your MATLAB and try to basically visualize what you did if you are familiar with the MATLAB. So essentially, if you think about the problem that we highlighted before, and then after running the optimization, basically they try to balance the completion time for all the flight paths. And not necessarily they all cover the same number of stars. And that's like after the optimization, the solution looked like this. And by doing the branch and bound technique, we also know this is really optimal solution. Even though we didn't do exhaustive search, we still can guarantee this is the optimal solution to this problem. So that's pretty much what I can say about the problem related to linear integer programming. Okay, so now let's look back to the question that we raised before regarding the inequality constraints. I think the question that we asked is about how do we examine whether the inequality constraint is active or inactive when you have many inequality constraints. Now, do you have a good answer to that? I guess some of you may say, now I get further confused. I think a brief answer is what? Do you have any efficient way to really examine those? A brief answer would be no. We simply cannot do that without losing something. We have to, for generic problem, basically if you got to verify whether inequality constraint is active or inactive, you got to what? Basically do your job, meaning you changed the problem from the continuous optimization to what? To some kind of a discrete type of combinatorial type of problem. And in that case, the problem is considered NP-hard. On the other hand, is there any way you can avoid that? Of course, there are possible ways to avoid that. I think some of you already made some suggestions, like putting a penalty function, even though that doesn't really change a lot, because later, I think some of you realize the unconstrained objective function may contain many penalty terms when you introduce the penalty function to the constraint, to the inequality constraint, and also equality constraint. Another relevant question is, when you introduce the penalty function, can you guarantee the solution to be always feasible? And I will put that as maybe new computer assignment, where you have to answer some questions related to that. And also, if you use some assumption on your feasible set, still by looking at just extreme points, if you don't have a good way not to avoid exhaustively search the extreme points, you cannot even handle linear program. Which means, for instance, simplex is considered the most successful method in operation research after World War II, and still it has been proved in the worst case to have exponential complexity in solving the problem optimally. So an alternative is to use so-called primordial interior point method, which I think in the textbook it's thoroughly covered, but I probably will skip certain mathematical rigors in the derivation later to talk about that. And this is just like a detour to the problem that when you change the linear program to linear objective function, linear constraint, but some decision variables are integer valued or discrete valued, then the problem becomes mixed integer linear program, and that's very difficult problem to handle. And because some of you are concerned about this is not covered in the textbook, so I provide some useful resources for just for your reference. And for this course, I don't really ask all of you to have very good understanding on what's going on, but at least I hope you understand about the basic idea to handle such a combinatorial problem. One technique that we mentioned is called the branch and bound, which is a very important technique. Even later when you study some other applications in artificial intelligence, in some other computer algorithm design, this is important technique that got to be mentioned in optimization. And Cplex and AMPL, you can basically study a little bit on the material, on the background, and how that's interfaced with MATLAB. Those things are important to when you have a real engineer optimization problem that involves discrete decision variables, like the example I gave on the task assignment, which you have like six aircraft to cover many stars and try to avoid obstacle, and then the objective is to minimize the whole mission completion time. And you got to search on all the possible ways to cover the stars, and the permutation on the task create the problem on the complexity of the optimization problem. So basically, that's pretty much about the main picture of optimization. And I know that maybe I didn't exactly follow the course syllabus, so that I just want to give all of you like the first landscape of the optimization. So far, we talked about what unconstrained and constrained optimization. I also talked about briefly about linear programming and what mixed integer linear programming. And next time, I'm going to talk about dynamic programming, which is considered a very important technique for discrete optimization. And also, it's not very thoroughly covered in the textbook, but I think it's very important optimization tool to solve real engineering problems. And I hope later I need to decide on some important subjects that I may want to cover, and also depending on the individual interest. One is about so-called global optimization technique, which includes certain heuristic algorithms like genetic algorithm or simulated annealing or taboo search or local search, or things related to how to jump from the local optimal solution to a global one when you have very bizarre objective function, when you have non-smooth objective function, when you have objective function containing many local maxima minima. And I may cover a little bit about convex optimization and its extension to geometric programming, and also even semi-definite programming. And also I could cover some aspect of like how some real engineering application can be cast into optimization problem. And that basically is application dependent. And also I can talk about some specialized optimization algorithms if some of you are interested. So basically I tend to get some feeling about, so far, how do you feel about the course material, what you would like to see, and what you probably don't want to learn, or what you think probably is not of your primary interest when you read the course syllabus. So basically, I would like to hear some feedback, just very briefly, from each of you. And of course, if you guys don't volunteer to speak up, then I have to take turns.
Yeah.
Okay, maybe Sarah goes first.
Optimization problems concerning networks.
Optimization problem concerning networks. Well, I think there are two different type of problems when you say concerning network. One is sometimes called network flow problem. And that's very specialized, I would say, mainly for some part of the discrete optimization technique, which probably deviate too much from the textbook. It's based on decision variables are continuous. So I will just cover that when I talk about dynamic programming. And there are other branches in not network flow, but some people call Metroid. If you heard about that name, then that means you probably are really sharp in optimization theory. And then in Metroid optimization, of course, it's mainly about how to extend this integer type of network structure to some abstract setting, which probably deserve a very specialized treatment, not in this engineer optimization course. So sorry, I probably cannot really meet the requirement on that one.
You want to cover any neural nets?
Neural network, well, I would say I tend to avoid talking specifically on optimization using neural network, because I would say it's just a special case of constrained optimization where, for instance, maybe if you want to learn backpropagation or some other type of gradient descent or algorithm, then you can learn that through some dedicated neural network course. I believe even in this department, maybe Dr. Bushra offered such type of neural network course before. I'm not sure if maybe in computer science department, Dr. Drew or some other professor may offer some neural network, some course that cover artificial neural networks, specifically feed-forward neural network. So I would say if some of you are interested, please choose your project topic to work on some optimization problem using neural network design. But no, I won't spend time to talk about how the neural network works to, for instance, as a function approximator, as a pattern recognizer, as whatever mathematical tool to model the nonlinear input-output relationship.
Yeah, I'm very interested in the practical problems, how to formulate. For example, this 5 plans to visit those objects.
Okay.
You gave us, you have the task assignment, you have the difficulties and result, but how to formulate this?
How to write that as an optimization problem, right?
Right, how to formulate and how to approach this problem. It's NP hard, yes.
How to write it down, I think you should know. Objective function, you don't know how to write it down? And decision variables.
And then what?
And then need to find a software package to solve your problem. Or maybe you need to write a software package to solve the problem.
If we don't, if we just use the techniques you told us in the class,
yeah.
Can we do it manually?
Yes, you can write your own branch and bound code. Mm-hmm. Basically, it will not be as good as this educational commercial software, but it should do equally well for this problem. That's why, for instance, if you happen to download the demo version of the software and run the example code, you probably can have better understanding how you can have your own design. And I do have computer assignment that ask you to program in MATLAB without my optimization toolbox, and then compare with the results with optimization toolbox. so that you have better understanding about specific algorithm.
Yeah.
But I will not really require each of you to write like a quasi-Newton method. I will provide you some sample MATLAB code so that if you want to know, you should read the detailed implementation.
Yeah. Another question is how many percentage of this textbook being covered? Because offline,
okay.
we want to read the book.
Okay, yeah, right now I would say when you read the textbook, you should read, of course, the first part 1, the mathematical background, and then you should read part 2, unconstrained optimization up to gradient method. And if you want, you can also read Newton's method, conjugate gradient, and quasi-Newton as optional reading when you try to understand better about those improved technique than the gradient method. And then the nonlinear constraint optimization part, you should read chapter 19 and 20, basically about both equality and inequality constraints. And later, I intend to cover global search algorithm. That's in chapter 14, and also linear programming, which is basically part 3. But I probably will not cover too deep into the interior point and simplex methods, which I would say I will save some time for just get familiar with the existing linear programming package, which you can easily write your problem in the standard form and try to choose the right tool to work for your problem. Because as an engineer, you probably don't really need to get into the details of, for instance, how to really do the affine projection for the self-deal interior point algorithm. But you need to know, for instance, the existing package, how to change your option to solve your problem more efficiently when you have maybe sparse property or some things that's related to your own linear program. Okay, any other suggestions or comments? Well, I don't enforce everyone to speak up, but if you don't say anything, that I would either assume that you understand pretty well about this, or you are not interested in putting like your own interest into my consideration in the rest part of the course coverage.
Dr. Chen?
Yes.
Okay, I'm interested in bundle adjustment, and I believe that the Levenberg-Marquardt, I don't know if I'm saying that right, is the technique that's used a lot for bundle adjustment.
Bundle adjustment, I'm not very familiar with that method, to be honest with you. So is that the optimization technique, or maybe particularly for some specific application you're talking about?
Well, I believe that the Levenberg-Marquardt modification, I think, of the Newton method is an optimization technique used for bundle adjustment. Okay. So really it's the optimization technique that I'm interested in.
Okay. Okay, yeah, I would say I consider like improved Newton's method, maybe for training neural network, for some other applications. And bundle method, yeah, I tend to think that's a little bit, if you think about some version that's also for constraint optimization problem, I would say it's a little bit advanced that I'm afraid that maybe at least half of the students will feel inclined to learn for certain mathematical rigors to approach to the technique in itself. So I would strongly encourage that if you have a project topic, propose to work on that. And also I think it would be nice that I will cover like the basic idea so that if you have good mathematical skill, then you can approach to understand better and maybe apply the technique to a real optimization problem. That's my suggestion. I hope that even though I admit that probably in this course I cannot cover that. Even myself, I don't know general bundle method. I only know a little bit about like improved version of the Newton's method for training neural network, which I personally feel it's just a specific technique to improve, to do a better local quadratic approximation for the improvement of the training. So basically that's what I feel. And of course, I would strongly encourage you to explore more if you are very interested in applying the technique for some specific problem for the term project. And right now, I have not specified any project assignment yet, but I would encourage all students think about what problem you want to work on for your term project. If it's something that of your own interest, maybe part of your own research, something that you see the real relevance, I feel it is better than the problem that I assign to you, that you have to do it. There's no other option. So please start thinking about that. Yes?
Okay, I don't know if it's really optimization, but I think so. It's about underwater communication, minimize the Doppler effects and the multipath loss. And also,
well, I would say later, I hope that for each student, or maybe some group of students, send me a brief write-up, like the proposal of what you want to do for the term project. It should not be overly ambitious, meaning that when you define a problem, I would like to see some example, or maybe mathematical description on the problem. Like in underwater communication, you cannot say my objective is to solve like the whole underwater communication problem so that the submarine can communicate with the ground, maybe with a data rate above certain so and so, because that's too, how should I say, that's too specialized, and also I cannot really penetrate to see the mathematical description of the objective function and the constraints, and also what technique you plan to use. So yes, that's a good application to explore, but I need more information at this point. So any other student wants to say a few words? Yes?
I'm very interested about global optimization and multi-objective.
Global optimization and multi-objective optimization techniques. Yeah, I will cover that.
And also, I hope you can give more examples, try to give more problem or examples, then show how to use which technique to solve those problems. Just some examples, otherwise.
Okay, yeah, let me put it this way. I think maybe as a graduate level course, we have to have some balance between the theory and the practice. Examples include, for instance, I can have examples like what I did last time. You have some simple objective function, you have simple constraint. We just do some exercise on how to apply the necessary condition to find stationary point. And also we can have examples like what I showed here, where you have the problem, and then you have like 5 airplanes to cover these stars, and then you need to fill in some gap to see how the problem can be attacked. And later, I'm going to have maybe some examples taken from my own research to say, well, in order to solve this part of the research problem, I need to apply that optimization technique. And sometimes we need to improve the existing optimization algorithm so that we can basically work so that it will work better for the problem that we are trying to address in that specific research area, that engineering application. So I guess I will try to provide as much detail as I can, but bear in mind, without your input, it is probably very difficult to satisfy your need. So.
For example, this example, we just know the problem, but how this problem translated to the
mathematical description. Yeah, that I would say.
You get the result.
Yeah.
want to tell more about the examples. For example, how to formulate.
How to formulate that, I would say you should be able to write it down based on what you learned from mixed integer program. And how to really work out this problem, that's hard because that requires you, for instance, to know some particular package. If not, then you need to basically try on your own branch and bound technique. For instance, if you just for this problem, if you want to write your own algorithm to solve this optimally, I would say it's a good term project topic that you can address without using any existing software package if you can solve this problem.
We can simplify just one class and two objects.
Well, then you can enumerate, that's fine. But still, how your algorithm will scale. For instance, I don't want to see some exhaustive enumeration in this problem. I want to see something more efficient. For instance, when you do your own branch and bound, maybe it's not as good as a commercial software solution, which maybe run 5 seconds and your algorithm run 5 hours. But if you get the optimal solution using branch and bound, it's okay. But if you say I have to do exhaustive search, that's not acceptable because after taking optimization class, you got to do better than that.
Yeah, so you suggest a way offline to try to formulate and write it down.
Yeah, and that would be one way of, for instance, finding some interesting term project topic. If, for instance, you think this is an interesting problem you want to work on. Of course, there are some technical details on how to really come up with a description that works for AMPL and call this simplex to get to the solution like this.
Right now, we are at the stage not using those advanced languages, especially designed for optimization, but how to use the MATLAB, even the optimization toolbox.
Yeah.
How to use that?
Well, that's not hard. I mean, if you explore a little bit on the help file, for instance, like fmin, I think, or fmin search, or fmin con, those are existing function calls. Then you just put your objective function and constraints into the proper form and put some initial condition and call the algorithm that you want to use. Then you get the answer. So that part, I wouldn't say it's very difficult. I already provided as much information as I can, even some example MATLAB code for the future computer assignment that you can easily run and get familiar with. Other than that, I would say it's difficult to combine both theoretical description and practical algorithm and also the real problem you are working on. So I hope that maybe after this round of interaction, I tend to think that if any of you come up with some good ideas, or maybe just some suggestions or something that you like, you hate, also you can use the course discussion forum to post your thread so that basically we can discuss and you can disagree with me on certain aspects of the course material. But I tend to hope that after some interaction, we can have better way to at least address the individual needs so that will help you understand the course material better. Of course, reading the textbook is also important aspect that I cannot cover all the single details in class. But I think for some of you who are mathematically keen to know the rigorous description of the conditions or things related to convergence property or things like that, because of the time, I probably cannot go into that deep level. But I will try to make some compromise if some of you are really interested in knowing those things.
Let me ask
sure.
Just like this, there are 5 plans. So 5 plans, no matter what kind of arrangement, there are 5 times. Like T1, T2, T3, T4, T5.
Yes.
For example, if this, we need to calculate the maximum.
Yeah, and then minimize that. Yeah.
Minimize the maximum.
How
to do that?
Yeah.
How to minimize the maximum?
Well.
5 plans.
One of the first classes.
First class, okay.
One of the first classes, yeah.
Yeah. You can change that into a standard way of doing this. But even if you just write it in the original form of the optimization, still you can think about what are the decision variables in your formulation. Do you need to introduce additional variables? Do you need to introduce additional constraints? Those things are not something that I can teach you because it's problem-oriented. And you have to look into the problem and know the techniques. For instance, can you convert this into linear program? Well, you cannot directly jump into that conclusion. After many trials, or maybe this, I already say it's NP hard, so you don't want to waste your time. But if you have a real engineering problem, there's no such answer to you like that. You have to find out. Like how you formulate the optimization problem is important, but knowing that the problem is very, very hard, how to solve that is also also an important issue because a lot of real engineering optimization problems are considered NP hard. And how are you going to deal with that? So I hope that's pretty much what I would like to learn, even though I think some of you may still feel a little bit shy to speak out. You can go anonymous when you post your comments on discussion forum. And I promise I won't trace back, even though some of you may want to say some criticism toward the course material, toward things that you don't like. I will try, of course, I may not change immediately, but I will try to accommodate some individual needs if you can open up and tell me how should I do. Okay, and thanks for your attention. So I will see you next week. And remember, the homework assignment and the computer assignment will be due next Thursday.
But next week, no class, right? No class. We have,
Well, after the